Hey everyone, have you ever stared at a math problem you got wrong and just could not figure out what happened? Well, you are in exactly the right place. Today, we're going to totally change how you look at algebra. We're not just going to be checking for errors, we're going to learn how to become math detectives.
So let's just kick things off with a big question. What is the #1 reason students get algebra problems wrong? Now, you might be thinking it's because they don't get some huge, complicated concept. But honestly, the crazy thing is, it's almost always the little, sneaky mistakes that trip us all up.
And I really want you to hear this. Making these mistakes does not mean you're bad at math. Not at all. It just means you haven't been trained to see the clues yet. And that's exactly what we're going to fix today. From now on, you're a detective. And these common mistakes, well, they're the mysteries we're about to solve.
Okay, let's get into it. Every detective needs a mission, right? Well, here's yours. To go from being a student who makes accidental mistakes to a super sharp investigator who can spot them from a mile away. You know, one of the best ways to get better at your own work is to learn how to find the flaws in someone else's.
So here it is, our most wanted list. For this first assignment, we are on the hunt for 3 of the usual suspects: distribution errors, sign errors, and just plain old arithmetic mistakes. Believe me, these 3 are the culprits behind pretty much every unsolved case in algebra homework.
To be a great detective, you gotta have the right tools. So let's open up our detective's toolkit and check out the essential gear we're gonna be using to crack these cases wide open.
This right here, this checklist is simple, but it is so powerful. Think of these 3 questions as your magnifying glass, your fingerprint kit, and your secret decoder ring all rolled into one. For every single problem we look at, we're going to ask, do they distribute right? Did they handle the signs correctly? And crucially, did they keep the equation balanced by doing the same thing to both sides?
All right, toolkits in hand. It is time to get to work. We're officially on the case, and we're about to investigate the evidence from 3 classic examples of algebra problems that have gone wrong. Let's see if we can spot the clues.
Our first case file is a real classic. We like to call it the lazy distribute. You know, it's that error that happens when you're maybe rushing through the very first step of a problem. Let's take a look at the evidence.
Okay, here's the problem. 2 times the quantity x plus 5 equals 16. And over on the right, you can see the student's work. It kind of looks like they're following the steps, but something is wrong from the very beginning.
Take a really close look at step 1. Use that checklist we just talked about. Ask yourself, did they distribute correctly? What do you see? I promise, the clue is hiding in plain sight in that first line.
And there it is. The student only multiplied the 2 by the x. They totally forgot to also multiply the 2 by the 5. Remember, distribution means you share that number on the outside with everything on the inside. So the correct first step is actually 2x plus 10 equals 16, which when you solve it, gives you the right answer. X equals 3. Case closed.
Let's move on to our next case. This one's called the magic minus. And it gets its name because a really important negative sign seems to have, well, just vanished into thin air. So here's the evidence. The problem is negative 3x equals 15. The student knew they had to divide to get x by itself. That's good. But their final answer is x equals 5. Let's investigate.
Let's pull out our toolkit again and think about the signs. The student divided 15 by negative 3. So, a positive number divided by a negative number, what kind of answer should that give you? Exactly. A positive divided by a negative is always negative. The student just dropped the minus sign, like magic. The correct answer here is x equals negative 5. See? Another case solved. The lesson here? Always watch your signs.
Okay, on to our final case file. Now this one gets right to the very heart of how we solve equations. We call it the inverse operations mix-up, and it's all about knowing your opposites.
The problem, x minus 4 equals 10. Simple enough. To get x all by itself, we need to get rid of that minus 4. The student decided to subtract 4 from both sides. Let's see if that was the right call.
This brings us to one of the most fundamental rules in all of algebra. To undo an operation, you have to do its opposite, its inverse. So what is the inverse of subtraction?
That's right, it's addition. To cancel out a minus 4, the student should have added 4 to both sides, but instead, they subtracted again. If you correctly add 4 to 10, you get the right answer. X equals 14. And with that, Another case is closed.
You've just solved 3 cases using the basic toolkit. That is awesome work. So now it's time to level up. Let's look at a couple of advanced techniques that the pros use to make sure their conclusions are absolutely airtight.
This right here, this is the ultimate move. It's called the plug-in method, and it's so simple. Once you have what you think is the final answer, just take it and plug it back into the very first original equation. If the left side equals the right side, you are 100% correct, no doubt about it. If they don't match, you know a mistake is hiding somewhere and you can go back and find it.
And here is maybe the single most important piece of advice any math detective can ever get. So many mistakes happen just because we try to rush and do 2 steps in our head at the same time. Don't do it. Slow down. Write every single step down. It creates a clear trail of evidence that makes finding mistakes so much easier.
So, we've gone over the tools and we've solved some cases together, but the real goal here is something way bigger than just spotting errors on a homework assignment. It's about building a whole new kind of mathematical instinct.
You see, the ultimate goal is to develop what I like to call an internal spell check. You know that feeling you get when you're typing and you just know you misspelled a word? We want to build that same feeling for math, that automatic sense that something just doesn't look right, so you can catch your own mistakes instantly. That's what being a master detective is all about.
Your initial training is now complete. You've got the tools, you've got the techniques, and you've seen the usual suspects in action. So the only question left is, what math mystery are you going to go out and solve first?